Friends, welcome to lecture 40 of the course Advanced Steel Design. We are working on estimating more examples on shear center. I will call shear center lecture 3. Okay. In this lecture, we will learn more example problems of locating shear center. So, example 2, we will take up a channel section . We know the shear flow, this is going to be so this is I call V1, I call this as V2, and we also know that this section has an axis of symmetry. So, the shear center will lie on this axis, let us say somewhere here. Let us assume that the load is applied at the shear center to avoid twisting of the cross section. We call the eccentricity or offset of the shear center from the face of the flange or the web at E. Let us say the depth of the web is D and the total breadth of the flange is B. Let us say the section has an uniform thickness T throughout. It is a thinned section and we already know the green line represents axis of symmetry. Shear center will have to lie, this is the shear center. Will have to lie along this line of symmetry. Let us take up element 1, this is my element 1, okay, and draw an enlarged view of this. Let us cut a section at a distance x measured from the tip and this is my dA. Okay. Let us call this thickness of the strip as dx and the CG of this dA from the shear center is d by 2 from the figure. D by 2 from the figure, and we know that this is breadth of the flange. Okay. Let us copy this figure and move to the next page. So, now let us write V1 will be integral tau dA, which is VA y bar by IT of dA integral. I want to find V1, which will be V by IT integral 0 to B, okay, dx into T is my dA y bar is d by 2, okay, and area of this is x into t, am I right? So, if I do this, which will become v by I t, I get again integral t square 0 to b d by 2 of x dx, am I right? Which now become v by I t, t square d by 2 x square by 2 0 to b, which will become v t square d by 2 I t b square by 2 b t square d by I t 2 I t b square by 2. Okay. So, I can now write v 1 as v t b square d by 4 I. Now, we can also say by symmetry this is equal to v 2, isn't it, from the figure. Further, look at this figure, I will copy this figure again. We can now say, taking moment about C, V into E should be equal to V 1 into d by 2 plus V 2 into d by 2, which is V 1. Okay. So, now V 1 is V t b square d by 4 I. V 2 is V t b square d by again 4 I, they are same. So, now I can say V e is equal to V t b square d by 4 I of 2, right. So, I can get E as 2 t b square d by 2, okay, into 2, sorry, d by 2. 2 t b square d square by 8 I, which will become t b square d square by 4 I. So, for a given section, if I know these values, let us say for example, B is 40 and D is 100 and T is 10. So, I can find quickly I for this, which will be 40 into 10 cube by 12 plus 40 into 10 into 45 square. Overall depth is 100. Okay, this is this is not 100, this is 90 of 2 plus of course I web, we neglect I web, okay. Which will be now equal to 40 into 10 cube by 12 plus 40 into 10 into 45 of 2 plus 10 into 80 cube by 12. So, I get I now. Okay. So, now in this equation I know T is 10 millimeters, I know B is 40 millimeters, I know D is 90 and I know I which is here. So, I can find E, and E will be the offset of the shear center from the CG. So, friends, we have a very easy example. These examples were easy because they had at least one axis of symmetry. Okay. So, the shear center was located in that axis of symmetry. So, it is very simple that if you have a problem where the section has got a symmetric axis, we can easily locate the shear center. Let us take up one more example, which is again simple, but slightly tricky in terms of its equation. Let us try to do that. We will take another example, we will call this example 3. We say there is a very common section being used in marine structures a thin section having uniform thickness. Okay. So, let us say the dimensions are marked as shown in the figure. This is B. Let us say this dimension is B1. The overall depth is H, all center to center. Uniform thickness T throughout. This section has an axis of symmetry. Okay. So, from this point let us mark the shear center somewhere here, and we call this offset as E. Okay. So, let us say the VR and V are acting here to avoid twisting of the cross section. So, now let us mark the shear flow. We call this forces. So, this is V1 and this is V2 and this is V3, this is V4 and this is marked as V5. Let us now start computing these internal shears. So, I want to compute V1. So, I am drawing an enlarged view of this. Let me cut a section of thickness dz at a distance z from here, and I am marking the centroidal axis or the axis of symmetry from here. Okay. And we know this distance is h by 2 from here, okay, and this was B1. Okay. Let us say what is my AY bar for the member 1, which is going to be Tz into Y bar will be h by 2 minus B1 plus z by 2. I am talking about this distance, friends. This is what I am writing it here. Okay. H by 2 minus V1 plus Z by 2. Okay. So, now if I say dA, that is going to be T dz. So, I have expression for V1, which will be V by IT AY bar. So, not integral 0 to B1 are my limits Tz h by 2 minus B1 plus Z by 2. I think it made it clearly Z by 2 of T dz. So, now I can do this integration and get V1 as, I am writing it here, Vt by I h B1 square by 4 minus B1 cube by 2 plus B1 cube by 6. Simplifying it, we get this as Vt by I h B1 square by 4 minus B1 cube by 3. That is my V1. Let us try to find V5. So, let me write this. So, V1 is Vt by I of h B1 square by 4 minus B1 cube by 3, which can be said as Vt B1 square by I h by 4 minus B1 by 3, which is V1, which is identically same as V5, we call equation number 1. Now, let us do it for V2, we will draw a separate figure. This is my axis of symmetry. Let us mark these dimensions. It is a thin section, so I am marking all the dimensions centra. This is B1, uniform thickness T. This is B, and we know this distance is h by 2. Let me cut a strip. At a distance x of thickness dx from here. Okay. We will also divide this into two parts. So, now I want to find V2. Let us find out what is Ay bar of piece 2, which will be two parts. Let us say B1 into T of h by 2 minus B1 by 2, that is this part. I mean, in fact, strictly speaking, it is this part. Okay, because the centroid of this will be h by 2 minus B1 by 2, am I right? Then the remaining part is x into T into h by 2, this part. And the CG is from here, which is h by 2. And we also know dA is T into dx. Can I now write the equation for V2, which is V by IT of integral of 0 to B, that is the elemental length, T into B1 h by 2 minus B1 by 2 plus x h by 2 of T dx, am I right? Now, integrating and substituting, we get V2 as Vt by I B1 Bh by 2 minus B1 square B by 2 plus B1 square H by 4, which is identically equal to V4. So, Vt by I B1 Bh by 2 minus B1 square B by 2 plus B1 square B square H by 4. B square H by 4. Having said this, let us try to find out the I of the entire section. Which will be equal to T H cube by 12. You can see the section. You can copy this. T H cube by 12 plus T B1 cube by 12 plus T B1 H by 2 minus B1 by 2 the whole square, AK square, parallel axis theorem. Okay. There are two such pieces plus B T cube by 12 plus B T H by 2 the whole square. Am I right? So, we have I here. Now, let us take moment about we call this point as O. So, V into E will be equal to V1 into B 2 times of that, because V1 and V5 are same, plus V2 into H by 2 2 times of that, because V2 and V4 are same. Okay. We neglect shear. V3. Okay. So, now V is a given data, this is a shear acting, force acting on the section. Okay. B, H are geometric data which is known. Look at this equation. If I know V, if I know V, if I know T, and if I can compute I can compute V2 and V4. So, not similarly, if I know T, if I know B1 and H, I can compute V1 and V5. So, in this equation, even V1, V2 are computed. So, I know V1, V2 also. So, I can easily find which is the offset of the shear center from the point O. Okay. So, it is very simple. So, we can take a quick example. Let us say, let B be 50, B1 be 20 or 30, H be 120 and T be 5 millimeters. Okay. All dimensions are given. So, I know all dimensions. Can you compute E? Therefore, locate the shear center. Okay, it is a very straightforward problem, there is no issue in this. Okay. Let us do one more problem. This is example 2, 3, we will do example 4. So, the cross section is drawn like this. Let me mark let us say this dimension is B, which is center to center. Let us take this dimension as B1 and this dimension as H. Let us say it is having uniform thickness T throughout. So, we know that this section has one axis of symmetry, this intersection is marked as O, and we mark this as my shear center, we mark this x and t as E from here. Let us assume that the shear and the reaction forces are acting at this point to avoid twisting of the cross section. Let us mark the shear flow now as shown in the figure. Say this is V1, this is V2, this is V3 and this is V4 and this is V5. Okay. Now, to locate V1, we know it is going to vary, say this is B1. So, integral 0 to B1 VA y bar by IB of dA. So, let us say area, we will consider a strip marked here. I will draw this figure separately. Okay. So, we will consider a strip at a distance z from here for a thickness dz, and I want to know the CG of this. from here. Okay, that is my y bar, right. So, let us say area is T into dz, sorry, T into z, dA is T into dz, y bar will be h by 2 plus B1 minus z by 2. So, let us substitute and get B1. Integral 0 to B1 V by IT Tz h by 2 plus B1 minus z by 2 T dz. Simplifying and substituting, I will get V1 as Vt by I h by 2 B1 squared by 2 plus B1 squared by 2 minus B1 cube by 6. Which is simplified further as Vt by I B1 square h by 4 plus B1 cube by 3. We will take equation number 1. Identically friends, this will also be equal to V5. Okay. Now, let us take the next part, that is V2. I will draw that separately. This is my line of symmetry. We know this is B1. I am marking the center line. We know this is B1 and the thickness is T uniform. I will cut a strip here at a distance x from here and let the thickness be dx. Okay. Let us hatch this portion. And I want to find the CG of this. Okay. That is what we want to find. So, let us divide this into two parts, and for our simplicity let us find V2. So, we know V2 is going to integrate, this dimension is B. So, 0 to B, VA y bar IT of dA. So, let us say what is A y bar for this problem. Let us do it in two parts. So, B1 into T into h by 2 plus B1 by 2, that is the first piece, plus T into x into h by 2, that is the second piece. Okay. This is my first piece, this is my second piece. And dA is the hatched strip, the blue wala, which is T dx. So, I can now substitute V2 as integral 0 to b v by it into t b1 h by 2 plus b1 square by 2 plus x h by 2 of t dx. Substitute, simplify, I get V2 as V t by I B1 H B by 2 plus B1 square B by 2 plus H B square by 4. We will call the equation number 2. V t by I B1 H B by 2, this is 2, okay, this is not Z. B1 square B by 2 plus H B square by 4. Now, I want to find the moment of inertia of the whole section. Let us copy this figure. So, we want to find the moment of inertia of the whole cross section about axis of symmetry. So, let us do that. I t h cube by 12 plus t b1 cube by 12 plus t b1 h by 2 plus b1 by 2 the whole square into 2 plus b t cube by 12 plus b t h by 2 the whole square into 2. So, I get I. Okay. Now, let us take moment about O. So, we know V into E is going to be equal to V2 into H by 2 into 2 minus V1 into B into 2. So, friends, V2 is a function of I, the geometric property. Okay. V1 is a function of I, geometric property. So, in this equation V2, V1 will have V, so V goes away, and for all the dimensions known, one can compute E. So, friends, we have learnt more examples of working shear center of symmetric sections. We have understood the use or the importance of shear center in the design. Okay. So, in the next lecture, we will start talking about shear center of curved beams. Suppose if I have a section which is curved, how do I locate the shear center? That is what we will focus on the next lecture. Thank you very much, friends. Have a good day.